Okay.
Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to welcome John Quigg from Arizona, from Tempe, who provided us with the shortest title ever, The Ladder. So some people buy the Stairway to Heaven, some people climb the ladder. It's all yours, John. Take it away.
Okay. Thank you. And thanks for this opportunity to speak. Um, yes, unfortunately, I had to provide an abstract. Otherwise, the suspense of the title would
Yes.
be more piquant. Um, but this will be a very simple idea. This will be one of these simple-minded ideas that actually goes somewhere. So you can see my co-authors. Matt Gillespie is a student of mine. Steve Kaliszewski and Dana Williams. So the idea is this. First of all, we begin with something that doesn't really look very much like a ladder, so don't worry about that. We call it a ladder anyway. It's an odd-looking ladder. So the rungs are slanted, so right away it's difficult to negotiate this ladder, and it doesn't look very stable. So we add vertical struts for
Mhm.
stability. Now at least it won't fall apart. And you're going to see this diagram a lot, so I hope you can tolerate that. So then we're slowly building how the ladder is going to work. We give direction to the rungs and struts so they up and to the right. And then we imagine that the arrows are maps, functions between sets, and that the diagram commutes. And it all rests upon a very trivial fact. If the vertical struts, the U and the V, are bijections, then so are all the rest, the F, G, and H. I'll give you a few seconds to convince yourself. You got it? Okay, here we go. So that's it. And now, have in mind, in this particular case, maps among ideal spaces of C-star algebras. So now, A, B, and C and D are C-star algebras. In each case, I of the C-star algebra means the space of all ideals. And then the rungs and the vertical struts are maps among the ideal spaces. And in this particular application, we imagine that the vertical struts are the real correspondences coming from Morita equivalences. So imagine that, for example, A and C are Morita equivalent C-star algebras, and then the real correspondence gives a natural bijection between the ideal spaces of A and C. And similarly, V gives we imagine the B and D are Morita equivalents, so V is a bijection, the real correspondence between the ideal spaces. And then again, since the real correspondence guarantees that the U and V are projections, once we know the Morita equivalences, then the routine observation would tell us that the F and G and H are all bijections. But we actually won't work with all ideals in this case. We have in mind that we were going to be talking about ideals that are equivariant under either actions or coactions of a locally compact group G. So throughout G will be an arbitrary locally compact group. And we'll assume that it acts or coacts on all of the C-star algebras. It won't be all actions or all coactions. In particular, in our case, on one side, for example, the A and the C might be acted upon by G, and then the other side, the B and the D, will have coactions of G, or the other way around. And we assume that all the actions and coactions are compatible in a way that makes the vertical real correspondences restrict to bijections between the invariant ideals. So just to be clear about this, if for example the group G acts on the C-star algebra A, then the set of invariant ideals are the ones that are for which the action restricts to an action on the ideal. In the same way, if there's a coaction, then an ideal is invariant if the coaction restricts to a coaction on the ideal. So that's the notion of invariant ideals for us. So if we had these vertical struts being real correspondences, then the F and G and H again would all be bijections by this, we call it the ladder lemma or something like that. So let's build the first application of this. Let's build a ladder. So we begin by carefully laying out the pieces on the floor. So if we start with A is a C-star algebra, and suppose that the group G acts on this C-star algebra by automorphisms. Then we continue. The next piece is the cross product, A cross G. It's the C-star algebra that has the same representation theory as the action of G on A. And then by cross product duality, which I'll talk about more as we go along, there's a coaction of the group G on this cross product. If G is abelian, then it would be an action of the dual group on that cross product. But in the non-abelian case, it's a coaction. And then we can keep on going. The next piece will be the cross product of the C-star algebra A cross G by this coaction of G. So we get a double cross product there. And again, by the general theory of cross product duality, because that's a cross product by a coaction, there's an action of G on that, a dual action. G acts on that. And again, once we have that, we have an action of G, we can continue. So the last piece will be the cross product by that action of G. So now we have A cross G cross G cross G. So the final piece, the final bit on the right is the cross product by that action of G. Okay, so those are the pieces that we'll use. And again, since that's a cross product by an action, there will be a coaction of G on that cross product. So going from starting in the lower left, A, and then continuing up to the right, up to the left, up to the right. We start with an action of G, and then a coaction of G, and an action of G again. Notice that the two pieces on the left, the two ends of that vertical separation, that these are actions, and similarly the two pieces on the right have coactions. So that's what I say. It's going to be mixed.
John,
so
sorry. John,
yep.
I have a number of students here in the audience. Would you mind explaining what you mean by that group gives you a cross product by coaction?
Yes. So here will be a lightning introduction to cross product duality. This all started in the 1970s with Takasaki. He did this with abelian groups and von Neumann algebra. So if you have an action of an abelian group, G on a von Neumann algebra, you can form the cross product von Neumann algebra. And then he proved that there is an action of the Pontryagin dual group of G on that cross product. And then if you form the cross product again, you get something that is isomorphic to the original von Neumann algebra tensor product with B of H, where H is the Hilbert space. And shortly after that, Takai did this in the C-star context. If you have an action of a group on an abelian group on a C-star algebra, you can form the cross product. There is an action of the dual group on that cross product. And again, the double cross product, well, this time it's isomorphic to the original algebra tensor product with the compact operators on H. So stably isomorphic. And so people were thinking, well, what if the group is not abelian? What do we do? So Takai teamed up with IMI, and they proved that if the group is just anything, then instead of an action of the dual group on the cross product, there's what's called a coaction. So this is kind of a categorical notion of duality. And if you have a coaction of the group G on a C-star algebra, there's a notion of covariant representations. So if you have an action, the covariant representation involves not only a representation of the C-star algebra, but also a unitary representation of the group. And with a coaction, everything is dualized, and the dual of a representation of G, think of it as being also a representation of the C-star algebra of G. So the dual of that would be a representation of C0 of G. And so covariant representations of a coaction involve a representation of the algebra and a representation of C0 of G, and they interact in a nice way that is compatible with the original coaction. And then a universal representation of such a thing gives you the C-star algebra called the cross product, and its representation theory is the same as the covariant representation theory of the coaction. So that's cross product duality. That's what cross products by coactions are. And in a couple of slides, I'll show you how we apply this in this case. Okay, so now we have these four C-star algebras, starting with A and forming successive cross products. And in each case, we can talk about the invariant ideals. So I sub G, the invariant ideals, either under the action or coaction in each case. So these are the nodes of the ladder. And now we have to form the maps to get the rungs of the ladder. So starting at the bottom left, Gx on the C-star algebra A, if I is an invariant ideal under this action, the action restricts to an action on I, so you can form the cross product I cross G by that. That's canonically isomorphic to a cross product of an ideal of the cross product. So an invariant ideal I has a cross product that gives you an ideal of the cross product. And that turns out to be invariant under the dual coaction. So we can continue. But more generally, if you started with any invariant ideal J of the cross product, invariant under the coaction, you could form its cross product, J cross G. And that would be an ideal of the cross product by that coaction. So the duality theory works just as you hope it would. And then finally, if you had an invariant ideal K of that double cross product, you can kind of remember where things are in the diagram. Invariant under the double dual action, you could form its cross product, K cross G, and that would be an ideal in the cross product by that double dual action. So at each step, cross products of invariant ideals give you invariant ideals. This gives us the rungs of the ladder. So these mappings FGH are just taking an invariant ideal in each case, forming the cross product to get an invariant ideal at the next level. So we have the rungs of this ladder. Now we have to build the vertical struts. So we start on the left-hand side. We have A at the bottom and the double cross product A cross G at the top. Now I tell you about the duality theorem in this case. The Imai-Takasaki duality theorem tells you that these two C-star algebras are Morita equivalent. In fact, it's a little bit stronger than that. The original theorem tells us that the double cross product is stably isomorphic to the original algebra A. That's almost the same as Morita equivalence. In fact, in the separable case, they're equivalent in some sense, although if you have a Morita equivalence and getting a stable isomorphism is a non-canonical thing, you have to make choices. But anyway, it turns out that for most applications, the Morita equivalence is the important thing. Knowing the stable isomorphism is not nearly so frequently required. So we have this Morita equivalence between A and the double cross product. It's usually called this theorem the Imai-Takai duality theorem for cross product duality, but I like to mention the name Takasaki at least once, and I'll tell you why. Many years ago, I gave a talk, this is more than 30, probably 40 years ago. I gave a talk, something involving cross product duality, and Takasaki was in the audience. And at the end of the talk, Takasaki made a comment. He said, you know, young people today, they don't mention the names of the founders of the subject. And he mentioned a few names, not his own, but I decoded this. I think he was perturbed that I had not mentioned his name. So ever since then, now I always try to mention his name at least once.
Even though Takasaki is no longer in the audience.
I hope not, because that would be awkward to have told that story with him in the audience. Yeah, but yeah, so I now it becomes a habit with me. I mention his name at least once. Well, so that's the left-hand vertical strut. On the right-hand side, we have the cross product A cross G. Remember, it has a coaction of G, and at the top, the triple cross product, it also has a coaction of G. So what did we do? We started with this C-star algebra A cross G. It had a coaction. We formed the double cross product. And the Katayama duality theorem says that those two C-star algebras, again, are Morita equivalent. It's a duality theorem for cross products that's completely dual to the Imai-Takai duality theorem. So there's a natural Morita equivalence between those two C-star algebras. And now we have the vertical struts. So the real correspondence in each case gives bijections between the ideals, but in fact, it restricts to bijections between the invariant ideals. This is a routine fact. It's not too hard to verify. It's because all the actions and coactions are related in appropriate ways. So the real correspondence restricts to bijections between the invariant ideals. In fact, it's in each case, it's a lattice isomorphism of the lattice of invariant ideals in each case. So we have the vertical struts now. Now we put it together, we have a ladder. We have the rungs, we have the vertical struts, and again, the vertical struts are coming from real correspondences between Morita equivalent C-star algebras, and therefore our ladder limit immediately tells us now that the rungs, the F and G and H, are bijections between the invariant ideals. In fact, lattice isomorphisms. So all of this only depended upon common tools in everybody's toolbox, actions and coactions, cross product duality, and the real correspondence between Morita equivalent C-star algebras. So the new facts are, first of all, these bijections between the invariant ideals when the group G is completely arbitrary, any locally compact group, and the technique of using the ladder. This is we believe, a new thing. There are similar bijections. This is not the only application of this. We could do the dual thing. We could play the same game, starting with the coaction of G on A, and then forming the cross product by the coaction. There's an action on that. We could form the cross product by that action. There's a coaction on that. We could form the cross product by that coaction. There's an action on that. And we could again build the ladder, and the ladder limit would give us bijections among the invariant ideals, but now we would be using the Katayama and the Imai-Takai dualities in the reverse order. Remember, if we started with a coaction, and then on the left-hand side, there would be the Katayama duality, and on the right-hand side, there would be the Imai-Takai duality for the associated actions. But it would be exactly the same process, playing the same game and getting the same result. Bijections between the sets of invariant ideals under the corresponding actions or coactions. The diagrams carry over to if we wanted to form the reduced cross products by the actions. So for an action of a group G on a C-star algebra A, you could either talk about the cross product, by which I mean the full cross product. It's universal for covariant representations of the action, or the reduced cross product, acting on this vector valued L2 Hilbert space, which is easier to control, but does not have a universal property. But nevertheless, reduced cross products are, in fact, they were used really before the full cross products. But anyway, there are appropriate versions of cross product duality, the Imai-Takai duality for actions, the Katayama duality for coactions. There are versions of those for reduced cross products by the actions. In fact, this is really a historical reversal. The original cross product duality theorems did deal with reduced cross products by actions. It wasn't until roughly 1990 that Rayburn showed us how to do all this at the universal level with full cross products and everything having universal properties. So now that in each case, there are two versions of the duality theorems, one using full cross products by the actions, one using reduced cross products by the actions. But once you have the cross product duality theorems, the latter works the same way, and it gives you bijections between the sets of invariant ideals. So effectively, we now have 4 theorems applying the latter method. I've eschewed opening the Pandora's box concerning maximal versus normal coactions. But now I'll just peek in the box a little bit. So again, with actions, you can either form the full cross product or the reduced cross product. Think of the full cross product as being the highest and the reduced cross product being the lowest. When you form the cross products, in each case, there is a coaction of the group on the cross product. If you form the dual coaction of G on the full cross product, there's a cross product duality theorem, but that depends upon the fact that the coaction on this full cross product has a certain property. It's called maximal. Think of it as being, it works at the highest level. For reduced cross products by actions, the dual coaction, again, gives you a cross product duality theorem. But then this type of coaction now has another property, which is, again, compatible with things at the lowest level. And for some reason, these are called normal coactions. If you look at the dual situation, the dual applications of the latter, starting with coactions, it depends upon whether you're starting with a maximal coaction or a normal coaction. If you're starting with a maximal coaction, form the cross product, then you take the dual action and you form the full cross product by that dual action and keep on going. On the other hand, if you started with a normal coaction of G on A, form the cross product, the dual action, then you would form the reduced cross product by the dual action, and then you can keep on going. So in each case, there are really 2 versions of the cross product duality you're using, either full or reduced cross products by actions, and correspondingly either maximal or normal coactions. There are coactions in between, the maximal and the normal ones, not called minimal for some reason. These are called exotic coactions. And there are versions of cross-product duality for these. This is explored by Buss and Echterhoff in a series of papers. Presumably, there would be a ladder application in those cases. We haven't examined this yet, but we think it probably would work.
John, can I ask
go
you?
ahead.
It's Ludwig. Hi. Can I ask you a question?
Hi, yes, go ahead.
So, but in principle, you could also, after taking first maximal, then perhaps you could take also reduced action of G. It would work, or at some stage on the second level of this ladder.
Well, the problem is that if you try to mix it like that, there would not be an appropriate version of a cross-product duality theorem to use.
Okay.
So in each case, you have to use the appropriate dual dynamical structure to plug into one of the known cross-product duality theorems.
Okay. Thanks.
Okay. So here's some current work. Three of us, Steve and Dana and I, are now finishing up a similar application of the latter method to ideals of Fell bundles over locally compact groupoids. So there are no C-star algebras here. We're just dealing with the Fell bundles directly. If you have a locally compact groupoid, like a group, but it has many identities, it's a small category where all the morphisms are invertible. Anyway, if it's locally compact, a Fell bundle just consists of Banach spaces over each groupoid element, and these Banach spaces, the elements of the Banach spaces can be multiplied or adjointed. How do you make a verb out of that? Adjoined? No, that wouldn't be right. It's awkward.
A native speaker, you tell me.
I'm not an expert on Fell bundles, but I just call it we form adjoints. Anyway, so there are these kinds of structures among the fibers, and you require that these structures are compatible with the corresponding operations downstairs. In the groupoid, you can multiply things and take inverses. So that would be should be compatible with the multiplication among the fibers of the bundle and the adjoints between the fibers. So Fell originally invented these things with groups, not groupoids, but he didn't call them Fell bundles. He called them C-star algebraic bundles. So now we did him a favor and shortened it to Fell bundles. But in the last 10, 20 years, this has been generalized to Fell bundles over groupoids, and we can play the same game. You can form a C-star algebra of sections of this Fell bundle, generated by continuous sections with compact support, and then complete it to get a C-star algebra in a similar way to what you do with locally compact groups. But you can also talk about algebraic properties of the Fell bundle itself without passing to the C-star algebra. In particular, this is something that was introduced by Dana Williams and Maria Ionescu within the last 10 years. There's a notion of ideals of a Fell bundle. You take a sub-bundle, so in each fiber you take a subspace, and you require these to fit together nicely to make a continuous bundle, and this should actually be a Fell bundle itself. It should be closed under all the operations, so it's a sub-Fell bundle. And if it follows up by multiplication in the appropriate way, then it makes sense to call this an ideal of the Fell bundle. So what Dana and Steve and I are doing now is saying, okay, so if we have Fell bundle over a locally compact groupoid, we can talk about ideals of this Fell bundle. Now, there is a way to form, I wouldn't call it a cross product, but a certain kind of product. In fact, technically, it would be called by now, I think it's called an action product of the Fell bundle by thinking about the way the groupoid acts on itself by translation. In the case of a group, you would be letting the group act on itself by translation. You can use that kind of structure to form a new Fell bundle. This carries an action of the groupoid on this new Fell bundle. You can form this semi-direct product by that action. That gives you a new Fell bundle. And then you can form, again, this action product. So you can get a ladder this way, and the vertical struts are actually Morita equivalent in a sense that in a way that makes sense for Fell bundles. There's a notion of equivalence between Fell bundles, and we've also recently proven that this gives rise to an appropriate notion of Morita correspondence. There is a correspondence between the sets of ideals of Morita equivalent Fell bundles. So we get the vertical struts, we have a ladder, and then we get bijections among the appropriate sets of ideals. So this is coming out soon. In fact, we just submitted this the other day. This, in fact, it should be on the archive by now. So bijections between ideals of Fell bundles and application of the ladder technique. Also in the pipeline, my student Matt Gillespie is going to give again a version of the ladder for actions and coactions, but now unifying this with using locally compact quantum groups. So it should simplify things. There will only be two versions, one for universal cross products and one for reduced cross products. But once you have quantum groups, you don't need actions and coactions dual to each other. They're all coactions of the quantum group. And so that should include the two original applications of the ladder that I talked about earlier. It's a can of worms using quantum groups. So this is going to take a while. There are a lot of little things that I like to think of it as the worst of both worlds. You don't have individual elements of the group anymore. And in the dual situation, you don't have a commutative C-star algebra. By the way, I noticed there's a chat here. Let me take a look at this.
I'll answer it.
Okay. Okay, very good. All right. Well, so I don't have to answer this.
Yeah.
Whoops, what am I doing? Oh, now you made me get off the rails here. Let me get rid of that. Come back here. In a situation like this, I apply the Microsoft method. I just get out of everything and then come back in. So I'm going to stop my sharing.
Okay.
I don't know what this picture is doing here. I'm just going to try to get, yes, there we go. And now I share again. Sorry about this. This seems to happen almost once every time I give a talk. Let me go to where it is. There it is. I make it full again. There we are.
Perfect.
Can you see it again now?
Yeah.
Okay.
We are talking business.
All right. So, yeah, I'm incompetent. All right. So these are, again, similar applications of the ladder method. The original application to bijections between invariant ideals of a C-star algebra and a cross product by either an action or a coaction, this is not completely new. There isn't anything really that well, I'll be in a precise way that in operator algebras, there isn't anything that's completely new. Everything is built, well, except for what von Neumann did. Everything von Neumann did was completely new. But since then, there's nothing completely new. There are earlier versions of these bijections between sets of invariant ideals. This was a couple of decades ago. Gutmann, well, I forget exactly when. Gutmann and Lazar proved something similar for group actions and coactions if the group is amenable, and that's a big add. This is a big assumption. Everything collapses when the group is amenable. There's no distinction between full and reduced cross products by an action. There's no distinction between maximal and normal coactions. Every coaction is both maximal and normal at the same time. And that simplifies things considerably. And so in that context, Gutmann and Lazar proved that for either an action or a coaction, there are bijections between the invariant ideals, but they used a quite different method. There is no ladder then, and we are sufficiently immodest to opine a more cumbersome technique. We think this ladder technique really simplifies things. So that's the amenable case. Somewhat later, Nilsson proved something similar, again, for group actions and coactions, for arbitrary groups, but using a different concept of what it means for an ideal to be invariant under a coaction. So it's not the same theorems. And again, Nilsson did not use the latter. She used techniques that were similar to Gutmann and Lazar. It actually involves induced representations. So there are precursors, but the theorems that I showed you are well, they're new in the sense that of being bijections between invariant ideals in the sense of invariance that I talked about. That an ideal is invariant under a coaction for us if the coaction restricts to a coaction on the ideal. Okay, so that's different from the notion that Nilsson used. But again, she did get bijection, so there's something interesting here. It would be interesting to compare and contrast our results with Nilsson. And so this is something we plan to do sometime. See what's going on there. Okay. I have to confess that I am essentially through with the results now. So we can discuss for a while or stop early. Our hopes and dreams for the future would be that we expect that this ladder technique will be applicable to other structures, not just for ideals. So this application of the ladder technique for invariant ideals, that's one thing, and it comes about naturally using the Morita equivalence and the Rietveld bijections, the Rietveld correspondences. But this ladder technique should be applied to other things. I mean, if you just have the ladder, so this diagram of mappings that are bijections on the sides and therefore bijections everywhere, that conceivably will have lots and lots of applications. So we implore you to go out and build new ladders and see what you can do. Who knows what wonders we might find. Every once in a while, you might build a ladder that leads to something wonderful outside. Okay, that's all I have. That's the latter technique. It's a very simple technique, but we think it will be applicable in many kinds of situations. Thank you.
But John, you still have 15 minutes, 50.
Yes, I know. So, you want me to give another talk? I could do that.
Yeah, of course. Go ahead. I mean, honestly, yeah, you can take the time. I mean,
Yeah.
it's a slot, and you can continue with whatever you want. I mean, as long as
Okay. I'll take you up on that.
yeah, go ahead.
Hold on. Let's see here. I'm going to show you a talk that I gave last year.
Mhm.
Um, let's see. I'm not sharing yet, so that
Yeah.
this will come about right now. I share,
Mm-hmm. Yeah. Now we
and
see. Yes.
yep.
Oh, that is very interesting topic. Yes, please.
Yes, P graphs, gauge
Yeah.
invariant uniqueness for P graphs.
Mm-hmm.
This is a paper that I wrote with Steve Galichewski, Nadia Larson, and Robert Hubin. And I
And
talked about this last year.
who is Robert?
Robert Hubin was a student of, I believe, let me get this right. I think it was David Pitts.
Mm-hmm.
But he's not in academia. He's uh, getting rich somewhere, doing probably computer stuff or something. I don't know, finance. So he's out of the game. But he gave us this gauge invariant uniqueness theorem, and then I decided, okay, let's give a new slant on this gauge invariant uniqueness theorem. So I'll go through this. This won't take very long. First of all, I have to tell you what a p-graph is, but that'll
Yes.
come in a couple of slides.
Mm-hmm.
But I mean, my uniqueness theorem, we have a homomorphism between two C-star algebras, and you want to know when is it faithful. Any such condition would give you a uniqueness theorem. A gauge invariant uniqueness theorem would mean that it's an equivariant for group actions. In this case, it's just we have a discrete group G typically, and we also require that this homomorphism should be at least partially faithful. So given some partial fidelity, you want to promote that to the homomorphism being faithful. So here is an example. If you have a directed graph with vertices and edges, a Kunz-Krieger E family where E is the graph, generating a C-star algebra B is faithful on the graph C-star algebra if it's equivariant for the so-called gauge action of the circle group T on C-star V and some action on the C-star algebra B. And the partial fidelity is it should be non-zero at every vertex. So that's the original gauge invariant uniqueness theorem.
Mm-hmm.
And it was subsequently generalized to K-graphs, higher rank graphs of rank K, where the action is by the K torus.
Yeah.
Okay, now here is an abstract, and this was what I wanted to inject into the circle of ideas. An abstract gauge invariant uniqueness theorem. I don't know who initially thought of this. It's just folklore. It was just in the air. If a compact group G, so I said discrete, I
No,
was,
wait, John. What does
yeah, go ahead.
GIT stand for?
What?
Gauge uniqueness theorem. Okay. Gauge invariant. Okay.
Yeah,
Yeah.
yeah, sorry, got you. Yeah, gauge invariant uniqueness theorem. If you have to write that more than 3 times, you look for a way to abbreviate it.
But John,
I
please.
misspoke it earlier. The group gamma is not discrete. It's in fact going to be compact.
But John, please be very careful with this word. If you change just one letter in this word, is a very vulgar word in Polish.
Okay, okay. I will be careful. Thank you. Thanks for the warning. And if you see this happening, tell me to stop sharing right away.
Okay.
Okay. So we have a compact group acting on a C-star algebra. Then a homomorphism from that C-star algebra is faithful if it's equivariant for an action and faithful on the fixed point algebra. This is an almost trivial theorem. You could prove it as an exercise. You use the conditional expectations onto the fixed point algebras that you get by just integrating the action, which you can do because the group is compact.
Yeah.
All right, so that's the abstract gayut.
May I jump in for a second? Can you go back? Yeah. So it's very, very interesting. I remember discussing and applying it with Richard Nest. If you have a short exact sequence of C-star algebras and you have an action of a compact group, and my point is that it can also be a compact quantum group. It's really, you don't need to have a classical group, but of course you need compactness. And then you can go to the fixed points of algebras, and you can have a commutative diagram of short exact sequences. So if you have a exact sequence to begin with, then you go to invariance of algebras, and it's again a short exact sequence. This is a very useful theorem. And I just wanted to emphasize that you can do it for compact quantum groups just as well.
That's a good observation, and in fact, that's maybe something in the future we should do this for quantum groups, compact quantum groups. So future work.
Yeah.
Or we used to do it. Yeah. So in the case of the gauge action on a directed graph, the appropriate notion of fidelity there was just that the vertex projections should be non-zero, and that actually implies that the homomorphism is faithful on the fixed point subalgebra under the gauge action. So it fits together. This is a special case. And now we bring in, as we must, coactions. If gamma is an abelian group, you can replace an action of gamma on A by a coaction of the dual group G, the dual of this abelian compact group gamma. This will be a discrete group G. So coactions of G are essentially the same as Fell bundles over G when G is discrete. So now I'm going to abandon the gamma and just take a discrete group G, possibly non-abelian, and I'm going to talk about coactions. And now we can form the, so it's really a Fell bundle over this discrete group G. So there's a canonical surjection of the C-star algebra of this Fell bundle A over onto the original C-star algebra A. The curly A, that's the Fell bundle. Its unit fiber is the C-star algebra A. There's a canonical surjection. You basically just evaluate sections at the identity element of G. So the fixed point subalgebra under the non-existent action of this non-existent group gamma anymore, this becomes the unit fiber A over the identity element of E. And this is the same as the fixed point algebra under the coaction. And now there is a maximal coaction of G on the C-star algebra of this Fell bundle that just takes anything lying over a group element S, anything in that fiber, A sub S, it takes it to A sub S tensor S. That's what the coaction does on the elements of the so-called spectral subspaces of the coaction. And in example, for K-graphs, the coaction comes from the degree functor from the K-graph lambda into n to the K. And here's the abstract gayut for coactions that Nadia and Steve and I proved not too long before this paper, so this is why we thought of writing this paper. If you have a maximal coaction delta of a discrete group G, then a homomorphism pi from the C-star algebra carrying the coaction from pi from A into B, it's faithful if it's equivariant for the coaction and a maximal coaction on the B, and faithful on the fixed point algebra under this coaction.
And now
The
wait.
dual version of the abstract Guyot.
So you're no longer talking any graph algebras or gauge actions.
Right, that would be just a special case. This is completely abstract. Any discrete group G and any maximal coaction delta of G on a C-star algebra A gives rise to this abstract gauge invariant uniqueness theorem.
Okay, it's very interesting. But can you perhaps at least, many people know what the K-graphs are, but many people don't. Could you at least give some flavor of what these K-graphs are? I mean, succinctly, but...
Sure. Here's a lightning introduction to K-graphs.
Yes.
A directed graph has edges and vertices, but the edges can be put together in a coherent way to make finite paths. And if you have a path with n edges, you say n is the length of the path. That gives you a mapping from the finite edge space into the non-negative integers, the length function on the paths. And now, instead of just the non-negative integers n, we take the product of n with itself k times, get n to the k, and now we want to have a category. So generalizing from the category of paths can be concatenated. So now we have a category and a functor into n to the k that has a factorization property similar to the way you can factor the length of a concatenation, a length of a path into, well, the first chunk of it concatenated with the last chunk. So the total length is the sum of the lengths of the two chunks. There's a version of this for functors into n to the k. If you have this factorization property, then it's called a K-graph, a higher rank graph. And it has a lot of the same flavor, the theory does, as ordinary directed graphs.
Thank you.
There are gauge actions of the K torus and so on. So here, now we go to P graphs, and it's capital P, and this is not an integer anymore. This is just a semigroup, well, actually a monoid, P, and it sits inside a group G. So G is a group, P is a submonoid, and we start with what's called a weakly quasi-lattice ordered group. So G is the group, P is a submonoid, and you talk about the monoid, you assume that it has trivial intersection with all its inverses. So you get a partial ordering on the group associated with multiplying on the right by something from the monoid gives you something bigger. And then the quasi-lattice ordered property is, I think this was almost maybe invented by Robert, I'm not sure. But anyway, two elements in the monoid, P and Q, if they're bounded above under this partial action, we assume that they have a least upper bound. That's the quasi-lattice, so the weak quasi-lattice ordered property. So we start with that. And then a P graph is a category lambda. And now the functor goes from lambda into the monoid P with this factorization property. So it's a direct generalization of what happens with K-graphs. If the degree, we say that D gives the degree. If the degree of a morphism alpha factors as P times Q, then alpha should factor uniquely as beta times gamma, where beta has degree P and gamma has degree Q. That's the factorization property.
That's what happens.
Analyzing directly from K graphs. Go ahead.
John, this is exactly what happens for the usual paths, right? If you look at the length of a path and then you can
Yes.
write this natural number as a k plus L, then you
That's
can
right.
chop this path into a subpath of
Yeah,
length.
so that's right. It comes directly. Yes, that's right.
And it's unique, and for the usual paths it's obvious. But now I'm having problems digesting this P. So am I to take that these high rank graphs are special case of P graphs?
Yes, where P would just be the
N to
the
K.
n to the K sitting inside Z to the K.
All right, all right. So this is a model of P. And why is it called P? P? Why is it P?
I don't know. I think the idea of, well, Nika originally talked about this kind of situation. He might have been guilty of introducing the letter P for this. I'm not sure. So, but it's not my fault.
Okay.
May I suggest an explanation?
Yes.
So if you have some ordered structures, then usually you have some positive kind of cone.
Uh-huh.
And this is typically denoted by P.
Okay, so it's P like positive.
Yes, so natural numbers inside integers are positive in this sense.
Yeah, I agree. That's probably the motivation. Yeah.
Yeah, but it was indecent, okay.
Yep. And there are some technicalities which I am not going to get into. So we require this this category lambda to have certain properties that make things nice. That they are not bizarre properties. They're just what you want to have things work out nicely. In particular, it's called finite alignment. But I'm not going to get into the guts of that. So again, the motivating example is a K graph. So the G and the P are Z to the K, Z to the K and N to the K. And now there are representations of this this P graph in C-star algebras that preserve the appropriate structure. And there are things called tight representations. This is the analog at this level of the so-called QUIGG representations of a K graph, which themselves are generalizations of the QUIGG E families, where E is a directed graph, so satisfying the QUIGG condition. So this is directly related to that, these tight representations. So there's a universal C-star algebra generated by tight representations, and that's the C-star algebra of the P graph. So every tight representation T into a C-star algebra factors uniquely through this universal guy, O of lambda.
And why is it obvious that it exists?
Because they could prove it.
Sure.
Yeah, so they generalize the techniques again all the way from directed graphs to K graphs, and then finally to this level using similar techniques, but then you have to work harder because it's an abstract situation, but it's the usual kind of thing. So it's what you would expect to be true. This is true at this level of generality, and now there is a coaction of the group G. Remember, we had the G and the P. So the group G has a coaction on this P graph C-star algebra O of lambda that takes morphisms S sub alpha, S has degree alpha in P, takes anything of the form S sub alpha into S sub alpha tensor D of alpha. That's an element of the group G, and that sits inside O of lambda tensor the C-star algebra of G.
Wait, so
An analog of the dual coaction. Go ahead.
G has no topology. G is discrete, right?
That's right, just discrete. Yeah, so this is the easy situation for coaction. So if it's a discrete group, everything is really just algebraic.
Yeah.
And that's a maximal coaction. So everything is at the universal level where things will work out for universal cross products and so on. There's a one-line proof.
Mhm.
It just tells you how to solve the exercise. You check that the universal C-star algebra of the Feld bundle A associated to this coaction is actually the same thing in disguise as the P-graph C-star algebra O of lambda. And then it all comes from the standard theorems.
Sorry, if you wouldn't mind to give
Go
another
ahead.
lightning course, could you now give me a lightning course about Feld bundles?
Yes. So
Okay.
we have a discrete group G,
Mhm.
and over each element of G, we have a Banach space.
Yes.
And so, of course, we can form the direct sum, and we get a Banach space of
Yes.
direct sums of all the. But we assume that among the fibers of this bundle, there is a partially defined. Well, in this case, I take it back. It'll be defined everywhere because it's a group, and so the group has. But the multiplication among the fibers should correspond to multiplication among the group elements, and also there you can adjoin, or you can take adjoints of elements in its fibers to get from one fiber to another, and that should correspond to the inverse operation in the group. That's a Feld bundle over a. This is what Feld spent a lot of years of his life developing.
Okay.
That's a Feld bundle, and there are the Feld bundle C-star algebra is universal for representations in C-star algebras.
Okay. Okay. Thank you.
So now our abstract Guyot immediately gives us a Guyot for P-graphs, a tight representation of this P-graph lambda into a C-star algebra B is faithful on the P-graph C-star algebra O of lambda if it's equivariant for some maximal coaction on B, and of course the gauge coaction on A, and faithful on the fixed point subalgebra of the canonical coaction delta on O of lambda. So that just comes, that's a special case of the abstract Guyot. This is unsatisfying though, because it's hard to check things on the entire fixed point algebra. So we don't want to have to do that. Here's how we fix it. We, well, not we, this was actually proven by Robert Hewlin. A tight representation T of this P-graph lambda into a C-star algebra B is faithful on the fixed point subalgebra of this coaction if it's what's called lambda faithful, and it just takes every element T sub alpha of the P-graph, well, the image of alpha into O of lambda. If it's this representation should be non-zero at all of those guys, so it should take elements of lambda to something non-zero. That's enough to make it faithful on the entire fixed point algebra, and so this is something you can check. You can just check on the elements of this P-graph lambda. And then we get the Guyot for P-graphs, the gauge invariant uniqueness theorem for P-graphs. A tight representation T of this P-graph lambda into a C-star algebra B is faithful if it's lambda faithful in that sense I just mentioned, and equivariant for a maximal coaction on B. So that's a version of the gauge invariant uniqueness theorem for P-graphs that is conceptually easier to handle than the previous versions of the uniqueness theorems that involved at the bottom end normal coaction. So this is conceptually simpler. I don't know if it's conceptually easier to handle, but very simple-minded theorem.
John, let me weigh in just very briefly. It's a very obvious comment, but let me make it nevertheless. It might sound confusing when you say maximal coaction. You might think that you have something whatnot in mind. That's just the obvious coaction you do, but then you do it for the universal tensor product. So
and that's really kind of what makes it maximal.
It's the algebra of a tensor product, the maximal one, okay? Because there are smaller ones, there are smaller norms. The universal is always the biggest. So when
Always
John,
the biggest.
yeah,
That's right.
I take maximal coaction, you might think, okay, but this is some type of a coaction that is maximal. No, this is the usual standard coaction.
Yeah, it's just that, but it has this maximal property that cross product duality works for the full cross product by the dual action.
Yeah, so this, I just want to make this remark to students because I just was thinking through algebra yesterday. So
yeah, so that's it fits in well with universal properties, these maximal coactions.
okay.
Okay. Now there were, again, nothing is completely original except what Vonneman did. There are earlier guides for p-graphs. Carlson, Kang, Shotwell, and Sims did it when p is abelian. And then there was no need for coactions because it's an abelian group. Well,
Yeah.
P is abelian, so the group G is abelian. It has a dual group and so on. Human himself, this was really the motivation for this entire investigation we're talking about here. He did it in the case where in this pair, the group G, the submonoid P, and he defined what it means to reduce to a minimal group. So there's a projection onto a pair where the group is amenable, and then again, things are nice. In the amenable case, everything collapses. There's no difference between maximal and normal coactions, no difference between full and reduced cross products by actions, and so on. So in the amenable case, things are a lot easier, and if your pair GP reduces in a technical way to an amenable group, then he gives a version of the guide for p-graphs. But now we don't care about that because we use maximal coactions and it works in complete generality. So again, both of the above are in terms of normal coactions. Once you have an amenable group, every coaction is normal, and you don't have to worry about you can represent things on Hilbert spaces you can see. So our idea was just to take advantage of the well-established theory of maximal coactions. Here's a lagniappe. So I have to now give you a lightning introduction to this word, lagniappe. This is a word that is used in New Orleans by the well, outside of New Orleans too, probably by Cajuns. It just means something a little bit extra. Here's something a little bit extra, a lagniappe with so-called co-universal algebra. So we have a Fell bundle A over a group G. There is a category of representations of this Fell bundle where a morphism is the homomorphism between the C-star algebras generated by the representations pi and sigma that transfers well such that it transfers the well, let's say it this way. So this sigma factors through the pi in the usual way. So it's a morphism from one representation to another. We can talk about a universal representation iota, so it's initial in this category. Every representation pi factors through it. We say a representation is A-faithful, where A is this fill bundle, if it's faithful on the unit fiber, A sub E, over the identity element of the group. And that makes it, because of the way fill bundles work, that makes it faithful on every fiber, A sub it. And then we have this lemma. A representation pi of the fill bundle A is faithful. If it is, then there's a coaction on the C-star algebra generated by pi that is compatible with the canonical coaction on the fill bundle. The coaction takes the image pi of some element A sub S in the fiber over S. It takes it to pi of A sub S tensor S, just like the dual coaction would. So in particular, the canonical coaction on the C-star algebra of the Feld bundle is the coaction associated to the universal representation iota. These faithful representations give a subcategory of all representations. A co-universal representation, this is the definition in some sense. Well, it isn't in the correct sense of definition, but it's one way to define this. It's a final object. It's a final object in this category of faithful representations. So it's a final object omega. It's a faithful representation, and for every faithful representation pi, there's a unique morphism from pi to omega, so it's a final object. Okay. And then the co-universal C-star algebra by definition is the C-star algebra generated by this co-universal representation. So again, think the co in the categorical sense, it's dual to the universal thing. This reverses all the arrows. This is co-universal. The standard coaction theory tells us that in our case, for a Feld bundle A, omega can be taken to be the regular representation of the Feld bundle into the reduced cross-sectional C-star algebra of the Feld bundle. And then we immediately have this theorem. A faithful representation pi of this Feld bundle is co-universal if and only if that coaction delta sub pi is normal. So again, this is at the opposite extreme, the bottom. Co-universal involves normal coactions. And then for every faithful representation sigma, the unique morphism phi from sigma to pi is a normalization of the coaction delta sub sigma. That's a technical term that means projecting onto something where the coaction is normal. And then we now characterize the co-universal representation. So we say a lambda faithful tight representation T of lambda is co-universal if and only if the associated coaction delta sub T is normal. And this is in some sense a general, well, another way of looking at the earlier theorems on co-universal representations. In particular, the regular representation lambda is co-universal, so the reduced C-star algebra of the p-graph lambda is a co-universal algebra of lambda. Okay. Now, this will be out of context, but I want to show you. I'd like to have a picture at the end of the talk. So, where to next? With this theory, where to next? Now, this was a talk I gave in Boston, and my best guess is that where to next would be there's a particular Irish pub in Boston, and here it is. So that was my idea of where to go next. And that's the end of that talk.
Okay, so
yeah, go ahead.
What I'm really craving for, in addition to Guinness, of course, what I'm really craving for is some examples. So for starters, could you give me some example of this GP construction,
yes.
not a high rank graph and not the situation? And also, I would like to see the C-star algebra, because can you go back to this empty slide? Because then I can write something. No. Just make this empty. Empty. Before the picture. Yeah, this is also fine, because I just need some space to write.
What slide do you want?
I want to, no, this one is fine. I want to write on your slide, so I need some space.
All right, good, yes.
This slide without the picture was great, because I had the full empty slide.
Lots of space, yes, good.
So let's do it very slowly. So if you take this.
Yes. So, yeah, go ahead. Or you're drawing something, good.
You see my drawing, right?
I do.
Everybody knows that the graph C-star algebra is the Teplitz algebra. Okay. Now, well, you can go further, and you can say you take some other examples, but this is everything is well known. But for instance, if you want to give a very simple example of a higher rank graph sister algebra, which is not anything exotic, you do the following. You just take the tensor, the Teplitz algebra, you take its nth tensor power, okay, and you divide it by the same tensor power of compact operators.
Mhm.
Yes, exactly. This is what I was explaining yesterday to my students, okay? Okay, so topologically, it's a quantum sphere, because when you think about the Teplitz algebra as the sister algebra of a quantum disk, its nth power, it's nothing but a two-dimensional quantum ball. And now if you think about compact operators as a two-dimensional open disk, then its nth power is just the inside of this two-dimensional ball. So what happens when we remove the inside of the ball from the ball? We get this boundary sphere, okay? So this is, in fact, what we used as the sister algebra of the 2n-1 dimensional Hilbert, that's a Danish name, very hard to pronounce, quantum sphere. And, well, it's too long a story to explain what a Hilbert, but Hilbert gives us a decomposition of spheres into solid tori. And this is where it came from. But my point is that this is a very, very nice and explicit example of n-graph sister algebra. And we use a paper of Aidan Sims and others, but Zielinski, 5 authors, I believe, where we use this gauge uniqueness, gauge invariant uniqueness theorem. It was useful for us because we knew that it was a higher rank graph sister algebra. So it's something very simple, something very tangible. So what I would like you to do is to give me this kind of an example of a p-graph sister algebra.
Okay, so I can do part of that.
Okay.
I can tell you an easy example of the pair GP, the weakly quasi-lattice ordered group. Namely, take the group to be any free group,
Okay.
any set of generators you like, and take P, the submonoid, to be the submonoid generated by the positive powers of the non-negative powers of the generators. So no inverses. Yes, take Fn and then P sub n, the products of non-negative powers of the n generators.
Okay, so all words without the inverses. Okay.
Yeah, all the words with no inverses. That's right.
Okay, I've got you. This is a nice
So
one.
this is not covered by the K-graph situation.
Yep.
So anytime you have a category with a functor into P, this P, that satisfies the unique factorization property, that would give you an example of a P-graph. Now, I don't have examples of those kinds of things. That I'm sure they exist in the P-graph literature, but this is a way to get examples that do not come directly from higher rank graphs.
Okay, and what would be the sister algebra?
Well, so you'd have to talk about representations of the P-graph.
Yes, please.
In this particular case, I mean, one you could consider the trivial P-graph. So just take P itself.
Okay.
With the identity map on P. That's a functor into P. It has the factorization property.
Okay.
And this is an example of something that was initially studied by Nika a long time ago. So the sister algebra of that would be universal for tight representations, and this is a version of the triplets algebras. And then if you require it to be tight, then it's a version of the quotient of the Toeplitz algebra by the appropriate version of the compact operators.
Aha.
So the Kunz-Krieger algebra of that.
Okay.
So if you look at the original paper of Nika, he'll have this some of examples, and then later on, Aidan Sims and some others. I think he teamed up with. Well, I referenced this earlier paper of Sims and Nadia Larson and Tilke Carlson, and I forget who else. Anyway, there will be some other examples of P graphs where the P is not necessarily n to the k.
Mm-hmm, mm-hmm. So if you'd like to read about it, it's Nika, right?
Yeah. Alexandru Nika.
Mm-hmm.
I think he's, well, anyway.
He's in, right? I remember he's in Canada.
Yeah.
Okay.
I don't know if he's retired by now, but yeah. So he did this stuff several decades ago. The initial version of this these Toeplitz algebras associated with quasi-lattice ordered groups.
Uh-huh. Uh-huh. Now, another thing which is kind of bothering me is the following. You see, it seems to be the case that there are so many different directions into which you can generalize graph sister algebras. And, well, of course, you need to do it because it's a very beautiful and tangible category, but it's also very tight, if I might abuse this word. How would you relate, because one of the obvious generalizations, this is what people do, beyond, of course, doing higher rank graphs, or even beyond doing quantum graphs, because you also have quantum graph sister algebras, I somehow would like to relate it to Kunz-Pimsner algebras. How does this, going into the P graphs and their sister algebras, does it have any relationship with Kunz-Pimsner?
Yes, in fact, I'm glad you asked that. So I want to assure the audience that I did not pay you money initially to ask this question.
Yes.
Yeah. So if, for example, with a K graph, the K graph sister algebra, it's not in any obvious way a Kunz-Pimsner algebra.
Mm-hmm.
In the case when K is 1, it is. The sister algebra of a directed graph can be viewed as the Kunz-Pimsner algebra of a naturally occurring correspondence where over the sister algebra of C0 functions on the vertex set, and where the correspondence is a completion of finite sums of well, finite linear combinations of edges. In other words, give the edge set the discrete topology, look at little c sub c of the edge space that completes to give a correspondence over C0 of the vertex space. And this was Pimsner's original motivation, I think, for defining the algebras that are now called Kunz-Pimsner algebras. But anyway, so there's no obvious way to do this for the higher rank case. However, there have been successes in this direction, but they go from the top down. They take a K graph and they notice that you can show that the K graph, the C-star algebra, is a Kunz-Pimsner algebra of a correspondence over a K-1 graph. And you get it by just taking away the edges of degree the 0,0,0,1 in n to the k, the e sub k. Take away those edges, that gives you a K-1 graph. There's a correspondence over this, whose Kunz-Pimsner algebra is the K graph C-star algebra. And then you could, if you wanted to keep on going down, you could then repeat that process, go from the top down. In a current project that I'm working on with with Steve Kalajewski, Valentin Diaconou, and Menesha Yuslu, we're doing it from the bottom up, starting with the situation that Pims knew about it. Every directed graph C-star algebra is the Kunst-Pinster algebra of a correspondence over the C-star algebra of functions on the vertex set. You form the Kunst-Pinster algebra. That is the C-star algebra of a one graph. Now,
Yes.
a K graph can be regarded as having K one graphs associated with it. Take all the morphisms whose degree is 0 in every coordinate except for the ith coordinate. That gives you a one graph. And you say you have K of those. So start with the first one. You form that's a K graph. That's a one graph. You form the Kunst-Pinster algebra of that. That's the C-star algebra of that one graph. And now you can repeat the process. Now there's a naturally occurring correspondence over that C-star algebra, whose Kunst-Pinster algebra is the algebra of the two graph that you get by edges of degrees only in the second dimensions. And you can keep on doing that. That process repeats. And after K steps, you get the K graph C-star algebra as an iterated Kunst-Pinster construction from the bottom up.
A kind of ladder again.
Yeah, sort of, yeah. It's an ascending step-by-step process. It's sort of a ladder. So this will be out sometime in the next year, probably.
And you also have topological graphs. One more thing, right?
That's right. That's right. For a topological graph, where the operations are required to be continuous and other things associated with topologies, there is no naturally occurring way of forming Kunst-Krieger relations of things. So that you take the C-star algebra by definition to be the Kunst-Pinster algebra of a certain correspondence. And this has even been done at the K-graph level, at topological K-graphs. This is done by Trent Yiend. But that turns out to be so ungainly that I don't think anybody is really working on that anymore. But it's something that could be done. You could carry this further.
Okay, so if you have topological K-graphs, do you have also quantum K-graphs?
I don't know of such a thing. Maybe.
Because it's quite
if there are people working on that right now.
Yeah, people
They've been listening to me.
Yeah, quantum games and so on. They like quantum. So it has some nice and tricky connections. Okay. All right. So let's thank our speaker for a very interesting talk. Thank you so much, John. And now we can begin real questions. So, Tomek, Adam.
I'm good.
Are you good completely?
Yes,
Adam?
I'm also happy.
All the way. Ali? Ali? Oh, you are muted. You are muted. You have to unmute yourself. You are muted.
Yes.
Okay.
Yes, I'm hearing. Yes, I'm hearing you. Do you hear me?
Yes, we can hear.
Yes. Thank you for the talk and for organizing this very. Sorry?
Yeah, just ask your question.
Sorry?
Just ask your question.
Do you hear me?
Yeah, we can hear you. You can ask your question.
No. I don't have any question. No. No. To be honest, the material of the talk, the material of you by a newcomer in this theory, I have some general question which is not particularly related to the talk. But if you allow me, I can ask some question about the graph CSR algebra, not necessarily related to the. May I ask the question, or in some other opportunity I can ask my question? I have some questions about the graph CSR algebra.
Yeah. So what's your question?
Do you hear me?
Yeah, we can hear you. Sometimes it goes down, but
Yes, my question is not related to the ladder techniques.
sure. It's fine. Just fire a question.
Yes. May I present my question?
Yes, go ahead.
He's frozen.
No, my question is about theory of graph CSR algebra. The question is that to what extent it is classified all CSR algebra who are isomorphic to a graph CSR algebra. Namely, what kind of CSR algebra can CSR algebra whose vertex and edge is coming from the projections and partial isometry. To what extent this question is obvious, to what extent this is already done? I don't know to what extent my question is obvious.
Himself.
I mean the classification of all CSO algebra which are isomorphic.
I'm sorry?
Sorry?
Oh, yeah.
I think we've got the question, Ali. It's really hard to hear you because every second word which you say is interrupted. But we've got your question, and with John we'll try to answer it. So, John, if you allow me to begin, and then you can elaborate, perhaps.
Yes.
It is a very natural question of what are graph sister algebras in particular, right? I mean, this is a very, very special and beloved case. So this is, as I said, a very narrow class. So John, correct me if I'm wrong. For instance, they always have to be nuclear, right?
Yes.
You see, then for instance, if you look at the K theory, K1 always has to be a free group.
Yes.
You cannot have any torsion in K1.
So, it has no torsion, that's right, yeah.
Also, basically, except for really trivial cases, you cannot tensor.
So the K theory is an abstraction.
Yes, exactly. Many natural sister algebras can be graph sister algebras because, for instance, the maximal classical subspace, the space of characters, cannot be more than a circle. You cannot have a two torus inside. Yeah. So they are not closed under tensor products. They are not closed under pullbacks. Many very natural, type 1, nuclear sister algebras, everything is nice and cool, SUQ3, quantum group sister algebras, they are not graph sister algebras. And then to accommodate tensor products, people went to higher rank graphs. And my questioning of, for example, was exactly trying to see what you have by going, say, now to P graphs. So you go beyond higher rank graphs, okay, and you go to P graphs, and do you get some new types of sister algebras or not? Because, for instance, one of the advantages of having higher rank graphs, which is not given to you in the usual graph sister algebras, is that you can do one more thing. You can theta twisting. You can do the theta twisting, okay, like you do with a quantum torus. Once we looked at these Heegard quantum spheres, because Richard was one of the co-authors and he's a master of theta twisting, he theta twisted everything. And our results went sort of like from classical torus to quantum torus, because everything we had like a theta twist of a higher rank graph algebra. So that's something which is afforded to you, not directly, but almost immediately from the definition of higher rank graphs. And then you go into much wilder category. And another partial answer to your question is that if you want to go beyond Elliott's classification program of unital, simple, separable, nuclear sister algebras, if you want to go beyond simple in any classification, then the best shot you have is with graph-sister algebras, and this is a fundamental work of Soren Eilers, who is a master of these things. Okay, so that's all I have to say. John, would you like to weigh in?
I think you pretty much covered, Peter. Yeah, so think of the original graph-sister algebras as being sort of analogs of the original Kunz algebras and the Kunz-QUIGG algebras. And then, yeah, so generalizing to higher ranks allows for a lot more types of sister algebras to arise.
Yeah, yeah. Okay, I think it's time to wind up. Do you guys have any questions? Young? No? We're happy. Okay, so let's thank the speaker again. Thank you so much, John. We stop recording.
Thank you.
Okay. Thanks for listening.